Good evening and welcome to Tinkering with Keithley. Well, 2024 will surely go down in my personal history as the multimeter year. Here, have another one. Though, strictly speaking, this one is a voltmeter only. But since it does support both AC and DC, I still want to call it a multimeter. A Fluke 893A. According to the revision dates and the manual I found for it, it was made from around 1969 to 1975 in this general shape. There was an equivalent AR version, where R means rack mount. Same guts, different case. Why did I get one of these in particular? Well, you can blame the Fluke 5100 Calibrator manual for that. To adjust the DC offsets of some of its amplifiers, such a meter was suggested. I'll go into details on why later. For now, let's see what awaits inside. When it arrived, it was in pretty beat up state. The case had lots of scratches and a bezel around the meter was missing, making it look a bit like the meter was pushed in. But it is supposed to be slightly recessed. It's just a piece of plastic trim around it that went missing in action. Opening the top cover first. It reveals the 4 PCB cards that make up the core functionality. But they are sitting beside their rails. Not a very good sign. Either somebody gave up on a repair job and didn't care anymore, or it experienced some severe impact. The power switch is a wafer switch that is extended throughout the entire unit. Clearly, Fluke wanted to keep the mains frequency in the rear. Removing the boards is relatively easy. Most of them are only held in by gravity and the connected wires. Oh, the sticker says Maizena reference diode is from 1979. Clearly, this unit has been maintained for some time. The second board I pull out has a rather large transformer on it. The third one is clearly one of the input stages. Extra shielding. Funny though, the line that enters the shielded part is a regular wire, not a coax as one would expect. That Teflon standoff hints towards very high impedance on the input though. The last PCB is trapped behind the power switch rod. I have to remove that one first. Now to the front panel. Whoops! I'm sure the knob should not pop out like this. But it confirms the heavy impact theory. Now to the lower half of the case. The final PCB is hiding out in here, again with additional shielding. You can also see a prominent deviation in straightness on the case frame. I keep getting the feeling that this unit was literally pulled from the dumpster somewhere. Getting the lower PCB out was annoying. The screws were tight and the threaded standoffs were spinning in the sheet metal. Lots of choice words were uttered. In the meantime, I continue with the outer case as good as I can. Maybe I have better access to the spin-offs, standoffs. The rear panel is the first to let go, but here the wires are soldered in and part of the wiring loom that goes through a tiny hole. I would have loved to keep that intact, but Fluke left me no choice. With the loom undone, I have at least enough slack to continue and see if I can unplug the remaining wires on the other side. The front panel also reveals some mechanical display shenanigans. The range switch mechanically moves some decimal points. I'm also surprised on how smooth the precision potentiometer turns after the front panel is removed. A quick glance shows that the frame is bent and that made the axle run at an angle against the panel. The front panel has seen better days for sure. It has scratches and discoloration all over. Ah yes, the broken axle from the function selector, clearly made from plastic for insulation. The shield on the bottom has some rubber-type material on it to protect the wires from chafing. But it has some nasty sticky goo on it now. Thankfully, that wipes off and leaves an okay version behind. Well, after removing the last tin on the rear, I have some access to the remaining standoff. And here we go. Finally that assembly comes out. Sheesh, it reveals a whole bank of precision resistors. Now to the meter movement. I'd like to peek into that to make sure that it didn't suffer any damage from the drop. Because the case is cracked in one part at least. And separating the last few bits from the rear panel. Say it with me. 3, 2, 1, recapping. I also gave all the wafer switches a good scrub and fresh lube. Some were easily accessible, some needed a bit of persuasion. But overall, I'm quite happy with the result. The meter movement looks okay. Nothing is binding up and the centering mechanism is responding well. I'll leave it as is then. The crack in the case needs some glue though. I tried model making glue because I know it won't haze up the plastic. It did work out fine. Reassembly time! Mounting the power supply components back to the rear panel. Note that there are a few holes in there that seem superfluous. These are for two options that could be fitted. One is a battery pack with integrated charging. This is also why the power switch is so complicated. It can switch from normal, charging, battery and off mode. But the battery modes are mechanically blocked on the front panel. The second option is a data recorder output, which would provide an isolated signal proportional to the meter deflection. My unit came with neither option. Cleaning the wafer switches was good in another way. Some of the wires were almost corroded through at the solder joint and they snapped off after a bit of handling. I'm sure these would have eventually caused issues. And another wire needs fixing. Straightening out the mounting bracket for the potentiometer. And two more. Oddly enough, the white ones seem to be the worst ones of the bunch. Could there be a chemical in the color? Checking up on the resistor section. It is a decade switching system that can provide precise fractions of the input voltage according to the switch positions. Connecting the wires to the meter movement was a bit of a fiddly matter. The manual shows a diagonal brace running from the front chassis plate to the horizontal one. The mounting holes are there, but the bar is missing in mine. So I made a new one. The first board to go in is the null detector. The second one is the RMS converter board. This one is missing in similar but DC only models that are available. And now, the reference amplifier. And last but not least, the inverter. and after tidying up the wire loom again, finishing the case. Which means taking care of the tins. Since the front panel didn't clean up as good as I hoped, I decided to repaint it. Following up with decals based on the original as a template. And a layer of clear coat to hide the edges of the decals and make them more durable. Fitting the decimal point and range indicator plates. The binding posts have a bit of wear on them, but they are complete and the inside is spotless after a bit of cleaning. So I keep the originals. I fabricated a replacement axle. This one is no longer clear, but it's still plastic. Should insulate well enough. Fixing the components to the front panel again was fun, if you're into pain. I did have leftover nuts from the calibrator, so I have an easier time with the wiring on the binding posts by pinching the eyelets between two jam nuts. Adjusting the knobs and display dials, taking the guesswork out of the calibration process. The binding posts were missing a shortening bar from negative to ground. I got a fitting replacement. And good news! I found a similar model, the DC-only version, as a donor device for cheap. It also includes the battery pack, so I can check up on that, some screws, and the hold-down bar for the PCBs that were missing, and most important of all, the bezel for the meter. Together with the painted tins, I consider the meter now complete. And to finish up the case, I also remade the stickers with the Fluke logo to cover up the screws again. Hopefully I never need to undo those again. Calibration involves lots of twiddling of knobs again. Instead of showing that, I'm going to explain what makes this meter special. The 893A is a differential voltmeter. This means that the meter internally creates a reference voltage, to be dialed in with the black knobs at the bottom edge, and then can compare the difference between that reference and the voltage applied as an input. It is thus perfectly suited to adjust voltages in circuit to a desired result. But why is that so much better than just reading the requested voltage? The reason is one of absolute versus relative values. If the target voltage is, for example, 10 volts, you can use a regular meter to read 10.0 volts, but only plus or minus some 10 millivolts maybe. Now, digital meters with more decimal places are better here, yes, but you still have to sacrifice precision for magnitude. If you measure the difference between a reference and a measured value, you can zoom in on that difference. If the reference is 10.000 volts and the input is 10.005, you can use the scale of the meter to zoom into the millivolts and read a 5, rather than some sub-needle width distance. Also, the input resistor can almost be arbitrarily high, making sure that there's practically no burden on the circuit under test. For pre-digital meters, this was an important thing. This type of meter basically does with voltages what a Wheatstone bridge does for resistors. You can of course either use the reference for trimming an external circuit, or you can adjust the reference until it matches the voltage on the input. Thus, you can also use it to precisely measure voltages. With a bit of math, you can also use it to measure high-value resistors. And I mean really high. According to the manual, anything between 10 and 10 to the power of 6 megaohm is suitable. So from 10 megaohm to 1 teraohm. I don't have any reference values that high, so I still haven't tested it yet. Now, since we measure difference between input and reference voltage, it would be nice to know the approximate value for the input. This is done with the TVM mode, which is short for traditional voltmeter, I think. Now, why would one still want to use such a meter today? One good reason I found would be the common mode suppression. If you need to check up on the DC level that is overlaid with an AC signal, or to word it differently, measure the DC offset of an AC signal, like you might need to do for amplifier adjustments, this device is still good for a run. Common mode suppression for DC, 120 decibel, and for AC, up to 100 volts peak to peak, 50 to 500 Hz, doesn't make a visible difference in the readout. This was key for adjusting some of the amplifiers in the Calibrator. And here's a quick example of checking up on a 5V power supply. Set the mode to DC, 5V reference voltage, connect the input and adjust the reference until the meter reads 0. Increase sensitivity and repeat. Then read off the reference voltage as a result. And that's it. Yet another meter for the collection and occasional use. I'm well aware that more modern gear would probably replace most of my devices and also be more accurate, but where's the fun in that? I hope you enjoyed this episode. See you next time! You can also see prominent deviation in... deviation. Oh my. Words are hard to read if there's letters missing in the script.